Hello, welcome back to Employability Improvement Training. My name is Ramachandran. I am from Buffalo Industrial Technology Research Institute. In the last video, we saw various computer architectures, von Neumann architecture, Harvard architecture, and modified Harvard architectures. We also saw about instruction set architectures such as CISC and RISC. We also saw about various micro-architectural features. The von Neumann architecture proposed by John von Neumann in 1945 had a central processing unit and an independent memory unit to store instruction and data. The central processing units specified by John von Neumann had a processing unit which had an arithmetic logic unit and processing registers. This architecture also specified a control unit which consisted of a program counter and an instruction register. Modern processors following John von Neumann architecture has some common components which are a control unit, arithmetic logic unit, and registers and interrupt exception handling mechanism. The processor controls everything that's going on in a computer. The control unit controls everything that happens within the processor. The control unit issues control signals that instructs various modules within the processor what to do. The control unit has an instruction decoder which translates the instruction which is currently stored in an instruction register into control signals for the rest of the processor. Control logic circuits generate the control signals that are sent around the processor to various modules. The control unit also has a timer circuit which creates pulses to synchronize operations within the CPU, and it works with reference to the processor clock. Modern processors has an arithmetic logic unit which performs operations such as addition, subtraction, multiplication, and division, and also Boolean operations. These operations are carried out using logic gates and adder circuits which we saw in an earlier video. Integer addition and subtraction are carried out using adder circuits, and Boolean operations are carried out using logic gates. Multiplication and division operations are performed in the processors using floating point unit circuits in the CPU. The arithmetic logic unit takes its data inputs from registers and control inputs about what operation to be performed on the data are received from the instruction decoder in the control unit. All the microprocessors have a set of registers evolving from the earlier days. The 8-bit processors had registers called AH and AL which could be combined into a 16-bit registers named AX. The 32-bit processors added another 16-bit to these registers and was named EAX, and in the 64-bit another 32 bits were added to the registers and called RAX. These smaller sized registers can be accessed in latest processors using their earlier names for backward compatibility, and the old programs can be still run on the newer processors. Program counter or an instruction pointer is a special purpose register which holds the address of the next instruction to be executed. It was called IP in 16-bit, EIP in 32-bit, RIP in 64-bit processors. The processor has another special purpose register called instruction register which holds the instruction that is currently executing in the processor for the control unit to decode. Apart from those special purpose registers, there are a set of general purpose registers. These registers can be used for many purposes, but historically the A register, which has name as AHAL in 8-bit, AX in 16-bit, EAX in 32-bit, RAX in 64-bit processor, is called as an accumulator and used in arithmetic logic and bit operations. Register B, which is also similarly named, was used as a base register which contained the base address along with base pointer. This register was used in extension of memory address. Register C was historically used as a counter in loop operations, and register D was used as a data register. There are a set of index registers which can be used in combinations with base registers to access larger memory. The source index and destination index registers were available in the processors. Stack registers are called stack pointer and base pointer are again used as index registers to support earlier segmented memory mechanism. There were a set of registers called segment registers. These are 16-bit registers and retained in the modern processors as 16-bit registers itself were used to hold the base addresses of various segments of a program. Code segment register was used to point the base address of the code segment. Combined with the instruction pointer, it points to the instructions that is to be executed. Stack segment register combined with stack pointer points to the current stack. There was a data segment register and extra segment register, F segment register and G segment registers. All of them could be used to point segments in data. In what is called a real mode operation, the segment registers combined with index registers directly point to the linear address or the physical address in the memory. In protected mode, the linear address could be obtained by adding a 0 to the address in segment register, adding to that the value in the index register. In the 32-bit processors, the segment registers, instead of having the address of the segment, contained an index into data structures called GDT, Global Descriptor Table, or LDT of the program, which contained information about the base address and offset, along with other information such as permission levels. In the latest processors, these registers are kept for backward compatibility but are not used as it was used in the earlier days. There is a status register or a flag register which was called E flags in 32-bit register and R flags in the 64-bit register. Each bit in this register is a flag. Each of these bits hold the status of various operations of an instruction which is getting executed in the processor currently. There was a carry bit which represented if the last operation carried out in the ALU had a carry. There is a parity bit which contained the value of 0, number of ones in the result of the last operation carried, and 1 otherwise. It had a 0 bit. This was set if the last operation resulted in a 0. There is a flag to enable interrupts which will let the processor to service maskable interrupts when set. There is a sign flag which had the value of the most significant bit of the result of the last operation carried out in the arithmetic logic unit. There are many other flags. Currently the last 32-bit of the R flag registers is empty. Current processors such as x86-64 architecture processors have up to 16 general purpose registers which are named R9 to R16 after these earlier named registers, and some of the RISC processors have up to 32 registers. In a computer, events happen asynchronously which require processor attention. For example, a button in a keyboard could be pressed which has to be interpreted and displayed on a monitor, which has to be done immediately as the button is pressed to give a better user experience by stopping whatever process that's going on in the processor. This is called interrupt. When an interrupt happens, the processor stops its operation and moves all the relevant data like instruction pointer and other registers to the stack and executes what's called an interrupt service routine, which will process the asynchronous event. These interrupts could be hardware interrupt, which are generated by devices, or software interrupt, which are triggered by the int instruction. A programmable interrupt controller generates the interrupt on behalf of the devices in the INTR line of the processor and puts a number based on which device requires processor attention. Interrupts could be non-maskable, which means it has to be serviced immediately. It can't be ignored. While a non-maskable interrupt is executing, no other interrupts can preempt the processor. And a maskable interrupt. The maskable interrupts can be stopped by changing the interrupt enable flag in the status register. Clearing in IF flag in the status registers ignores interrupt in the INTR line. When an interrupt happens, the processor stops the currently executing process after pushing all the relevant data for that process into stack and loads an interrupt vector, which could be the address of the interrupt service routine or an index to the interrupt vector table. In x86 architecture, in real mode, the interrupt vector table or IDT is stored at the beginning of the physical memory, and it contains 4 bytes of memory for each of the interrupt, which points to the location of the interrupt service routine for servicing that interrupt. In protected mode, a register called interrupt descriptor table register contains the base address and the limit. The 8-byte IDT contains the segment selector and offset, which points to the interrupt service routine for servicing that specific interrupt. Performance of microprocessors. The performance of a microprocessor can be measured by the time taken by the processor to execute a program. Clock speed of a microprocessor can indicate its performance. It is a simple measure but is not very accurate. If the number of instructions executed per cycle along with clock rate could give an indication of its performance. Microarchitectural features improve the number of instructions executed per cycle. Features like pipelining, out-of-order execution, superscalar issue increase the number of instructions executed per cycle by supporting parallelism, so they can improve the performance of a processor. There are some standard tests available which also could give an indication of a processor's performance. Let us take a look at the specification of a processor. We will take Intel's Core i7-4770 processor as an example. This processor has 4 cores and it supports hyper-threading. It can run 2 threads in each of its core. So the total number of threads it can run are 8. The clock speed is 3.4 GHz. With turbo, the clock speed can go up to 3.9 GHz. It has L1, L2, L3 cache in the processor. It has a 32 kilobyte data and 32 kilobyte instruction cache per core at level 1, and it has 256 kilobyte per core level 2 cache and the 8 MB level 3 cache. This processor supports SSE extensions. SSE extensions are streaming single instructions multiple data extensions. These are basically a set of 128-bit registers which can store multiple data on which the same instruction has to be executed. So in a single cycle, a same instruction can be executed on multiple data. These instructions support heavy graphics processing and other processes which can run in single instruction multiple data mode. This processor supports 64-bit instruction set architecture and has 16 general purpose registers and 16 SSE registers. This is a very powerful processor which supports many other technologies like Intel's virtualization technology and others. That brings us to the end of introduction to microprocessor. To recap, the invention of binary number system by Leibniz paved the way for processing numbers in binary in the modern computer. Francis Bacon's invention of the ability to represent alphabets of languages in binary form led to the development of ASCII and Unicodes, which form the basis for processing language in binary form in modern computers. The invention of Boolean logic by George Boole and the later development of Boolean algebra as a branch of mathematics, and Shannon's demo implementing Boolean algebra and binary arithmetic using electronic switches and relays led to the development of logic circuits. Logic circuits carry out most of the internal operations of a modern computer. Inventions in the field of electronics, starting from vacuum tubes to ICs, led to many developments in digital processing. and the invention of large-scale integration and very large-scale integration integrated chips gave the ability to put many transistors on a single chip, and the microprocessors became more powerful and efficient. Alan Turing, by his invention of Turing machine, paved the way for theoretical computer science. Till 1940s, the computers were mostly program controlled. They were able to do only a specific job. In 1945, John von Neumann proposed the stored program computer model. He published an architecture for computers. He said that the program for a computer can be stored in an independent memory and processed in a central processing unit. Von Neumann architecture had a single bus to access instruction and data from the main memory. This led to inefficiencies in the processor while it is waiting for instruction and data to be fetched on the same bus. Harvard architecture resolved this by having independent storage for instruction and data and accessing them over separate buses. A modified Harvard architecture relaxed this separation. It let processors to work as pure Harvard architecture while accessing cache and work as a pure von Neumann machine when accessing the main memory. We saw that in the earlier stages of evolution of microprocessors, the goal was to provide easy programmability. The instruction set architecture used during that time had many complex instructions. These instructions were non-uniform in length. They took a lot of time to execute. This resulted in the processor remaining idle while data or instruction is fetched from the main memory. The RISC architecture resolved this by having simple fixed length instructions which were highly optimized in the hardware and implementing complex instructions as subroutines. Many of the latest CISC processors have adopted the RISC features in their implementation. Accessing data and instruction from main memory is a slow process. After a lot of research, many micro-architectural features were implemented in the modern processors. They improved the efficiency greatly. Some of the micro-architectural features we saw are pipelining, out-of-order execution, cache superscalar issue, and multi-threading. We also saw that the modern processors following von Neumann architecture have some common components which are control unit, arithmetic logic unit, registers, and we saw about the interrupt and exceptional handling mechanism in the modern processors. I hope this gives a basic introduction about the background of microprocessors. We will see computer architecture where we cover system bus and memory management and other devices which form a computer in the next class. Thank you.